Information about the exam. That's a rather large standard deviation. This is a skew right, skew left distribution. But that's a reasonable average. So I'm not unhappy about the exam. If you are unhappy about your exam, then you should be coming to see me at some point. Your exam grade is not your final letter grade at this point in the course. You should see Canvas to know exactly where you are overall at this point. I did post the key. If you've got questions, hey, what did I lose points for here? Go look at that, see what I was looking for, and then come talk. Okay, moving forward. I've got all these probability distributions. I've got all these ideas. I've got all these confidence intervals. My goal is to make good decisions and to use my data to do that. How? Well, the goal is really cyclical. I start with some assumption, some hypothesis, and I decide whether or not the data I've collected support this hypothesis or not. So I need to have a question I'm trying to answer. I need to have an idea about what should or should not be able to be shown, and I write this hypothesis up. I gather some data, and I do a statistical analysis. I compute some things and test some things, and then decide, does this data back up what I'm saying or not? Page 318, figure 9.1, shows this sort of data-driven cyclical decision process. I have an idea. What do I think should be going on? Let's get some data, calculate something and decide. And then if I need to, revise my idea and do it again. If I think these two things are related somehow, I should be able to back that up. Now, the assumption I make, my hypothesis, is usually referred to as the null hypothesis, H0. Most of the time, the null hypothesis is there's no real difference, or there's no effect here. There's nothing going on. Nothing to see here, move along, forget it. Its opposite is called the alternate hypothesis. Some books use HA for alternate. Some references online I've seen write H prime. I'm going to use H1 because that's what this textbook uses. Now, in order for me to have a good hypothesis set up here, I need two things to be true. I need these two hypotheses to be mutually exclusive and completely exhausting. Exhaustive. I've heard those terms before. That was back in chapter 4 or 5, somewhere back then. What does it mean for things to be mutually exclusive, completely exhaustive? Jacob.
Mutually exclusive. I don't fully remember. I think it's something to do with like they're both like independent. And not independent, but like, they both represent their own thing.
They represent their own thing, but not just their own thing. There's no possible overlap between them. Our idea of independent had something about probability in it, right? Which came from our ideas about sets. That's where mutually exclusive comes into play. Those sets have no overlap. They each are their own thing, separate from one another. There's no possible way to have anything in between. That means one or the other, not both. Completely exhaustive.
So that's like there's no like possibility left.
So these two statements, H null, H0, and H1, should cover everything and leave no stone unturned and not have any overlap between them. Okay, let's run with that. I go to court. Here is a charge filed against me. I am guilty or not guilty. There's no in between. And there's no other option. I'm doing a drug test. NCAA came to town. That's the athlete. Is the test positive or not? There's no in between. I've got a security system. I enter a code on a keypad. Does it let me in? Yes or no? I walk up to a door, tap my ID, beep, or not. There's only two options. Okay. In order for me to set up a problem in the first place, I'm going to have to write those out. I'm going to figure out which one I think is unusual enough that it will require evidence to be true. And that is where the next piece of this comes into play. I need a decision rule. Once I have gathered my data, how do I decide which of these is right? Now, in a jury trial in America, the standard for proof of being found guilty is beyond a reasonable doubt. That's instructions from the judge will help you make that decision. There's going to be a drug test. There's going to be some sensitivity to that test, right? I gotta go and they gotta watch me pee in a cup, and then they gotta take it and they gotta run it through the lab and all that fun stuff, and then they come back with a report. But somebody in that lab put some reagents in something and tested, and okay, this showed up or it didn't. My security code on my card was recognized by the door because it's connected to the database in IT, and that is acceptable to open this door. Now, Remember, I said I made an assumption about my situation, my null hypothesis. I am not going to be able to prove my hypothesis. I can only say the data I have gathered supports it or doesn't. Now, if my data is opposing H null, since my options are mutually exclusive and completely exhausting, if it opposes H null, it's supporting H1. My alternate must work rather than my hypothesis, my null hypothesis. The best part about this is I can do these tests over and over and over. Except in court cases, there's this thing called double jeopardy in the United States. You can't be charged for the same crime more than once. So if I have an idea and I go out and I gather data, I could go out and gather data again, make sure I get the same result twice in a row. I go out and gather data a third time. I can repeatedly gather data to ensure that I am getting the same decision every time that backs up my idea and strengthens the support of it. It never proves it. The only way in which you can do a proof is to do something that is purely mathematical. And that's not what this course is about. Now, once I've made my decision, I can then revise my hypothesis. I can take some actions. I can decide what the right thing is to do next. Okay. So, in general, I have something I'm trying to show is supported or not by the evidence. I gather my data and I make a decision. There are two possible outcomes. I make the right decision or I F it up. Yes? Either I got it right or I got it wrong. But let's think about what could happen. I need to make up a hypothesis for us to use at the moment. Let's go back to the court case idea. You are being charged with something, I don't know what. Either you did it or you didn't. I don't know which of those is the case. That's what the trial is for. But either you did it or you didn't. In the court system, the assumption is that you are innocent. So my null hypothesis, there's nothing to see here. Everything's cool, you're innocent. The alternate hypothesis, you did it. You are guilty. But here's what happens in the trial. The trial goes through, and the trial says, we think this person is guilty. We reject the assumption of innocence. Or we say, okay, no, we don't have enough in front of us to say not innocent. Now that isn't, we're going to say the alternate is true. We're going to say there's not enough to support. I fail to reject this. Now, in this case, this is the right choice. In this case, this is the right choice. This is a mistake. In our situation, this would be putting an innocent man in jail. Remember, the assumption is you didn't do it, you're innocent. But I reject that. You get found guilty by this trial. This is a bad thing. We're going to call this a type 1 error. Because I said, hey, something's wrong here, out. If I think about the drug test, the assumption is you're clean. My null hypothesis is you are a clean athlete. And I reject that assumption. I say you're disqualified. They found traces of drugs in your system. That is referred to in the drug testing industry as a false positive. I'm going to use that same terminology here. If I reject the null hypothesis when I shouldn't have, I made a false positive error. On the other hand, this is also a bad choice. This is also a mistake. I should have failed to reject. I should have said there isn't enough evidence to disqualify you.
That'd be type 2 error.
Yeah, that's the opposite. Type 2 error. False negative. Now, in my drug testing terms, that means whatever drug you took, you got away with it. In my trial, that means a guilty person did not go to jail. And I will quote one of our founding fathers, and the idea of the jurisprudence system, who said it is better for 100 guilty men to go free than to send one innocent person to jail. So that clearly tells me that now I've forgotten who that is. Franklin, Jefferson, Paine? I don't remember who said that. I apologize. In that person's view, a type 1 error is a lot worse than a type 2 error. In the drug test, I'm allowing a dirty person using drugs to compete anyway. If I think about the door swipe, the null hypothesis is it should let me in. I'm a legitimate user. I should be able to get in this door. Type 1 error is all of a sudden this door doesn't recognize me. I should be able to get in, but it says no. A type 2 error means somebody who has an invalid card got in anyway. So I deny an authorized user or I allow an unauthorized user. Which type of security error do you want to make? Makes a difference, right? And if you're in cybersecurity or in physical security, this matters as to how tightly you control access to your location. Questions? Okay. The way we design our tests. I'm going to gather data and I'm going to decide on a test. And that test is going to have some probability associated to it. So I'd say, I only want to commit this kind of error, a very small amount. So let's call the chance that I make a type 1 error. Let's call that alpha. That is the probability that I reject my null hypothesis given that that is true. I made the mistake. See how that's a conditional probability? And then I'm going to make the same definition down here. I'll call beta probability of a type 2 error. Now, that's this box. If this was a probability table, then each row and each column should add up to what? Because these are mutually exclusive, these are the only possible decisions I can make.
That'd be fair to reject the zero with two reject.
Yes. But the total across that row here. I don't know that for sure. But I do know that the total in the row should be 100%, right? Because either it was true or it was false. Yes? And I chose let's reject. These two numbers should add up to 1. So if I think about 1 minus beta, that is the chance I rejected when it was false. That was a good decision. That's this one right here. We're going to call that the sensitivity of our test. So I can make a drug test more sensitive, right? Detect smaller and smaller amounts of that drug. I can make the magnet in the door sensor more sensitive. It'll detect the field in my chip closer and closer. This is the chance I got it right. This is also sometimes called the power of our test. I like sensitivity a little better. This is the chance that I used a test that didn't make a false hypothesis, right? Because H null is false. So I'm making sure I don't let the innocent people go to jail. Yes, that's a good thing. I don't want innocent people to go to jail. I should have a powerful system here, a sensitive test. Problem. If I want this number to be big, I want this number to be small. I need beta to be small. But tests that have high sensitivity trade off with alpha. As I just said earlier, it is better for 20 guilty men to go free than 1 innocent go to jail. I'm letting some people go to jail. I'm letting people get away without going to jail when they could. Oh, crap. More powerful tests. Lower beta. But to lower alpha, I need to make rejection harder. I need some sort of stronger way to think about, should I really reject this null hypothesis or not? And now in the jury system that is beyond a reasonable doubt. That's a really strong idea. But to do that means I may let false null hypothesis. You were innocent, but it's false. You were really guilty. I'll let that go through. So there's a real trade-off between alpha and beta. Now, let me put this in terms of something you've all had to deal with. How many times has the smoke detector gone off? Fire alarm goes off in the door. Your apartment building, your house. Not an uncommon occurrence, but not a rare occurrence, right? How many times has there actually been a fire? A sensitive detector will catch and prevent fires. It'll alert hey, there's something going on here. But the more sensitive it is, the more likely a false positive is to occur. Hey, there's something going on. No, there isn't. Somebody just made popcorn. A sensitive carbon monoxide tester will do the same thing. You need to get out of this building or you will suffocate. A COVID test. The more sensitive a COVID test is, the more likely you are to be told stay home because it showed up as a positive test, even though you just barely had a virus in you. It was really sensitive of a test. That means healthy people stay home when they don't have to. So there's a trade-off. The more I increase my sensitivity, the more likely I am to have an issue. Most of the time we are concerned with type 1 errors more than type 2, so we are willing to take a significance choice. We're willing to pick alpha. Rather than picking beta. And if we want to make beta smaller, rather than changing the sensitivity of the test, we just gather more information. Now, sometimes gathering more data is hard. Larger N might increase my cost, might increase the time it takes to do this. I am going to pick alpha, my significance, at levels that are going to reflect a probability that you've probably already heard. I don't know, maybe I'm okay with alpha being 10%. Maybe I'm okay with alpha being 5% or 1%. Wait a minute. Those sound like the numbers we did in our confidence intervals, right? 90% confident, 95% confident, 99% confident, meant there was 1% on the outside, or 5% on the outside, or 10% on the outside. This is the same idea. And that's why we use alpha in this last chapter. Because that alpha is this alpha. Problem number 5. What is the consequence of a false negative in an inspection of your car's brakes? The null hypothesis is the status quo. Things are okay. Nothing to see here. Your brakes are fine. Hang on, Leo. Your brakes are fine is the assumption. A false negative. Let me go back to my chart. False negative. My null hypothesis is false, but I didn't reject it. The hell does that mean for me out there in the real world? Yeah.
Maybe a type 2 because like you're accepting it breaks the agreement really are to lead to a crash.
Consequences crash. Potentially. I have said I did not reject your null hypothesis. Your brakes fine. But they're not. Oh, you go down the front drive and you end up in the 131 parking lot. Oops. Okay. So now, here's my idea. What I want to do is make a decision rule. Some way that I can say, here's how I know I'm going to reject the null hypothesis. Here's how I know I'm going to not reject it. And I need this rule to be based on statistics. So I'm going to step up my idea here. And instead of just talking about any hypothesis, let's talk about a statistical hypothesis. A statistical hypothesis is a hypothesis that I make about a parameter in my population. Something I want to understand what's going on in my population. Maybe I'm trying to be looking at a proportion. Maybe I'm looking at an average. But somewhere in there, I'm going to have a statement about some parameter. Now, almost all the time, the parameters we are looking at are exactly that, means and proportions. A hypothesis test is a statistical decision between my statistical hypothesis and its alternate. Excuse me. My goal is to be able to do an analysis about my parameter and decide if my hypothesis is supported or opposed. So, I have some experiment I'm running, and I think the average number of times people succeed is 5. I go out and I run this experiment 35 times, 73 times, 112 times, doesn't matter. I run this experiment. I then calculate my average. So I go out, I run my experiment, I get my X bar. I believe that X bar should be close to 5. So now I need a way to decide, based on my X bar, is my average 5, or am I wrong? And the average is something other than 5. How am I going to judge that? I'm going to be able to judge this based on the sampling distribution for X bar. I can look at the standard error. I can look at my confidence interval. That's the method by which I can judge if my assumption is right or not. This is the basic idea behind all statistical analysis. My hypothesis is some claim about the mean, or maybe a proportion. So I'm going to make a benchmark. In my example, the benchmark is 5. Now that benchmark value in and of itself, I don't know where that comes from, except to say it usually comes from prior experience. It usually comes from understanding some industry standards, targeted values, product specifications, something specific about my object, test, product built into that. For example, I know that at the NFL Combine, they make you run the 40-yard dash, right? And they have a set of standards. People should be about this fast, based on what position they're applying for, right? You don't expect your left tackle to be running like a wide receiver. I know yay much about football, people, so please forgive me. But I'll have a benchmark and I'll say all of the tackles should be running around this fast on the 40-yard dash. All of the wide receivers should be running around this fast. I remember a news story about the Combine this year about somebody who set a record in the 40. Oh, this guy's going to go places. Clearly, you went 40 yards really fast because they had an idea of where people should be. That's the benchmark value. It comes, as far as I can tell, out of thin air. Somebody has to provide that to me. Maybe there's some industry standard. If I'm making bottled water has to have a maximum level of chemicals that are allowed in it, right? There's a maximum level of chlorine that can be in the finished product when I bottle the water. There's a maximum amount of lead. There's a maximum amount of mercury. All of these things are required by EPA standards. Am I meeting those standards? Light bulbs. We have fluorescent light bulbs over our heads. Anybody know the crazy chemical that's involved in fluorescent light bulbs? Technically, if one of these bulbs breaks, this room just became a hazmat area. There's mercury in those light bulbs. The same mercury that you used to make thermometers out of. There's minuscule amounts of mercury, but technically, if you break a fluorescent light bulb, even a compact fluorescent light bulb, you're supposed to cut away the carpet the light bulb fractures landed on and throw out the carpet and the pad underneath it for potential mercury contamination. So the EPA insisted that home use fluorescent light bulbs have less and less and less mercury in them. I need to know, if I make light bulbs, am I meeting that standard or not? If I'm not meeting that standard, the EPA can come and fine me. There's my error, right? I said I'm meeting the standard. They test some bulbs, say, no, you're not. I could be on the hook for a couple $100,000. When I talk about my null hypothesis, there are really three different ways to write a null hypothesis. And I can think of it in the way I just said. I'm making light bulbs. There is some maximum value of mercury in my light bulb. So I could say, oh, my null hypothesis is either I'm more than that value. We're going to call the benchmark value mu0 for a mean or pi0 for a proportion. I could say that I'm exactly at that value, or I could say I'm less than or equal to that value. Now, I know for the light bulbs, I probably want to be here. But let's say I'm making protein powder over at the factory for, I don't know, GNC. Then I probably want to be here so that I have a minimum level of protein in each tablespoon or scoop or whatever, right? I set up there in my example, I thought the average was equal to 5. That's this version. Each of these has a corresponding alternate hypothesis. If this is my null, that my average is bigger than or equal to my benchmark, what's my alternate? Mutually exclusive and completely exhaustive.
Would be mu greater than u1.
No, I don't have another benchmark. I only have one benchmark. I need the opposite of this sentence. If I tell you it's bigger than or equal to something, be less than that number. If I tell you it's equal to, then the opposite would be not equal to. And if I tell you it's less than, the opposite would be bigger. Okay. Here's the interesting part about this. Let me think about the light bulb example. The light bulb example is over here. The light bulb example says, my light bulbs have less than the maximum amount of mercury in them. They go off and test the amount of mercury in my bulbs, and they come back and say, no, you have more. Number line. More is to this side, yes? More's off to the right. I'm going to call this a right tail or right side test because the alternate hypothesis is to the right. I use the phrase right-tailed. Some books use the phrase right side. Well, if that's the case over there, what's the one all the way over here? What's this one? If I say I've got at least this much protein powder,
This would be a left tear test.
because low numbers are on the left side.
This would be 2 tear center.
Because it's either equal or it's not. I don't know which direction it is. Now, it's actually even better than that. Because I'm sampling, right? And when I sample things, what's the distribution I get from sampling? 3 cheers for the central limit theorem.
These are skewed, it's on right.
But when I sample, the more I sample,
More accurate I'm getting.
more it looks like my normal distribution. Yes? If I do sampling, I should get a picture that looks like this. When my samples are big, when I take enough samples, or if I have a normal population. The way I decide which of these I'm going to support is based off of alpha. So here's the neat part. I decide on the sensitivity. Sorry, the significance, not sensitivity, significance. Remember, I want the chance that my null hypothesis is wrong to be alpha. That was our definition of alpha. I rejected it, but it was true. I made the mistake. So I want the chance of rejection to be whatever this number is. I want the probability of H1 to be less than alpha. Now, what does that mean? If I'm doing a right tail test, it means I want a number that will cut off a portion of this graph that is exactly alpha big. And then I want to know where the number I come up with is in that section or not. Page 325. These are the 3 most important pictures in this chapter. If I am doing a right tail test, this little shaded region has size alpha. If the number I come up with is in here, reject. If I'm doing a left tail test, it's the mirror image of that picture, isn't it? But if I'm doing a 2-tail test, I split it in half. Remember, we used Z alpha over 2. Bing, 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 bing. I'm gonna use those Z values again and again and again. And I'm gonna call those critical values. And we will pick up how to use them when we get back from Easter. Have a wonderful break, and I will see you soon.